Function notation is a strategy for writing functions that puts the emphasis on the name of the function and the identification of the independent variable. At this point, we have plenty of experience working with equations that look like this: y equals 5x minus 3. Function notation says that because that is actually a function in the conventional sense, there's an input followed by an output, and those input-output relationships are unique, that we can re-identify this using function notation. So function notation works like this. Instead of naming the rule y, we're going to name the rule f. We're going to give it a name. Typically, if it's in a context, you'll name it after the context. If you know it's dollars, maybe you name it D. If it's about houses, maybe you name it H. You try to get the name to follow the context. But normally, if you don't have a context around the problem, you simply just name it F, G, and H. F, G, or H. Those tend to be the most popular names. After you identify the name of the function, we follow that with an indicator in parentheses for what the independent variable is going to be. Now, this might seem a little unimportant, that obviously the independent variable is going to be x. But what about if we had a situation where there were multiple variables on the other side? Maybe those other variables are representations for a constant that we should look somewhere else for in the problem. If we know that x is our independent variable, we know that's where our inputs are going to go, and we finish writing the rule the exact same way that it was written before. In the event that we want to graph a function, the most fundamental way to graph a function beyond technology is to make yourself a table. It is a table consisting of the independent variable in one column and the dependent variable or the name of the function in the other column. And you simply can just choose some x values to get an idea of what the graph is going to look like. So if x is 0, then we would write that f of 0 is 5 times 0 minus 3, which is negative 3. F of 1, which is 5 times 1 minus 3, is 2. And f of 2, which is 5 times 2 minus 3, which is 7. We should notice that as we went up by 1 over here, we went up by 5 over here. That's exactly what our slope suggests. And then we place those points on the graph. Now, the advantage to doing this particular equation, just as a way of getting started, is you know that this graph is going to be linear. So regardless of what points you pick, picking 2 or 3 of them really isn't going to make that much of a difference because you have this idea of what it's going to look like already. And then ideally, it's going to follow that curve, excuse the non-perfect straight line, but it should be a perfectly straight line going through those 3 points. We knew going in that this was going to be linear, so our choices for the x didn't matter so much. Well, what happens when we don't know that something is linear, or we're not sure that something is going to be linear? Or in fact, in this case, we don't know. We're going to rename our function g, followed by x squared minus 2x minus 3. Now, in your previous experiences in math class, you might know that this is going to be a quadratic. This is going to take the shape of a parabola. You might not necessarily know where. There are techniques for determining where the parabola is going to sit, where the parabola's axis of symmetry might be, and we have some ideas about where those things might be. But the truth is that we're operating under the assumption that we don't know anything. So we have x and g of x. Now, if we really don't know anything about this function or have any idea of where it's going to sit on the coordinate graph, there's some rules that you might want to follow when it comes to choosing your x's. Typically, the recommendation is that you're going to choose 5 different x's so you can get an idea of the full picture of the graph. When you choose those 5 x's, one of the numbers that you choose should definitely be 0, and we're going to talk about why in a second. You should also pick a couple of negatives, and you should also pick a couple of positives. Now, if you know that the numbers that are in this function are significantly larger, maybe it said 50x squared minus 300x plus 700, these 5 numbers probably aren't going to do you that good because you're going to have something that's going to be scaled out way beyond that. You're not going to get an idea necessarily of the shape. 0 might be helpful, but maybe you want to choose much larger numbers. But since we're in this small space here, x squared minus 2x minus 3, those numbers are all generally pretty small, we choose x's that are generally pretty small as well. So we're going to evaluate g of -2, g of -1, g of 0, g of 1, and g of 2. Remember what this is saying. Here's the name of the function. Here's the number that I'm going to input. So let's get the easy one out of the way first. 0, -3. I know that point needs to be there. We value that point as much as potentially any other point because of its role as the y-intercept. Anytime your input is 0, you are identifying the y-intercept. Because of the uniqueness of a function, the fact that an input leads to an output, that is the only y-intercept. There isn't some other magical place where we're going to find another y-intercept. So it benefits us to find that y-intercept straight away right from the beginning. And as we evaluate the others, it is just a matter of simple substitution. So we can start at the bottom since those numbers are positive. They tend to be a little bit easier. Let's input 2. So we have 2 squared is 4. 4 minus 4 is 0. And then we get another -3. We get the point 2, -3. Okay, we get the point 2, -3. And then we input 1. 1 minus 2 is -1, minus 3 is -4. We can start to see maybe how this parabola is starting to come together. -1, -1 squared is 1. That's a +2, so that's 3, 0 here. Feel free to check the value of any of these if you're not sure. And then -2, -2 squared is 4. 4 plus 4 is 8. 8 minus 3 is 5. So we have -2, 5, which is up here. And here we have the problem with graphing these by hand. In an ideal circumstance, I would have graphed perfect symmetry. I would have graphed right around the vertex that's at the bottom of the graph. I would have centered the points. I would be able to mirror points. I would be able to do the kinds of things that would go into graphing a parabola, a shape that we know is symmetric. The difficult part of that is that we don't necessarily know all of the details of the graph. All I have right now are these 5 points. But based on the numbers that you choose and as you graph these functions, you can get a rough idea of what it's going to look like if you follow through those 5. We expect, because it's a parabola, that it's going to be a smooth curve, and we get that look. Now, I'm not 100% sure at this point, and no one is, but there's a pretty good guess that that's where the vertex is, that bottoming out point of the graph. And if that's where the vertex is, then we should expect a symmetry line right through here. The same idea and the same logic would work for absolute value functions. It has that symmetry that goes down the middle. And because it has that symmetry that goes down the middle, we can assume that this gets copied over on this side. And you have this nice parabola look that goes like this. But as was suggested in analyzing this example, yeah, we made some choices about -2, -1, 0, 1, and 2. We're not sure that those were necessarily the best choices. It looks like I would have been better off maybe picking -1, 0, 1, 2, and 3, because 3 would have got me the symmetry that I might have been looking for had I been looking for the parabola. And then we lucked out on top of that because the axis of symmetry is actually on one of the numbers that I chose. What happens if it isn't? So that's what goes into all of the thinking behind graphing these by hand. That's why technology ends up being so important. It may not be a perfect graphing, and you might not be able to detect it perfectly, but you at least get an idea of what it's going to look like, and then hopefully help you find some of those key vertices, highest points, lowest points, relative maximum, relative minimum that we've talked about in other lessons. So some things to know, things to remember about function notation. First is one that we've already talked about. F of 0 is the y-intercept of the function, and there will only ever be one. You lose your function, the descriptor as being a function, if you had more than one y-intercept. That means 0 would have to map to 2 different places, and that's impossible. So there's only going to be the one y-intercept. Contrast that to the x-intercepts. The potential exists that there could be more than one. Here we had 2. one over here and one over here. One of them was at -1, and I'm going to guess the other one was supposed to be at 3. But there can be more than one x-intercept. There can be an infinite number of x-intercepts. I'm thinking of a number of trigonometric functions that you'll see in later courses where it's constantly crossing the x-axis based on how it was constructed. So expect there to be and anticipate there being more than one. If it fails when you substitute a number in, then that number is not in the domain of the function. And we looked at that a little bit in the last lesson with domain and range. You get something that was supposed to be there and available to you, but is not. That's okay, that happens. But then you have to understand that doesn't mean you did something wrong. It just means that that particular number does not fit in the domain of the function. And lastly, what's coming for function notation? Well, we're going to add, subtract, multiply, and divide, create fractions, compositions. We're going to be able to put functions together. So there's a lot happening in with these functions that goes beyond simply just saying, well, inputs and outputs. Inputs and outputs are good when you want to do the graphing that's involved here, but they are not valuable by themselves. We want to get working with them and combining them and thinking about situations where we might want to combine them. And that's where the add, subtract, multiply, divide, creating fractions and doing compositions will come into play. Compositions is the one that typically trips people up, but it's just a matter of understanding what an input actually means. You are inputting something into a function, and so the creation of a composition is just an extension of that idea.